In this section we're going to look at calculating magnetic fields from complicated distributions of current. But first let's have a reminder of what we've seen before about magnetic fields. Let's say we have a wire with a current I flowing down it. Now this is a conventional current. Conventional current means you're assuming it's positive charges that are moving. In reality, of course, it's electrons that are moving and they're moving in the opposite direction, but we can ignore that for the moment. If the conventional current, the putative positive charges are going this way, then there's going to be a magnetic field, and the magnetic field will do rings around the wire. Which way did they go? Well, for that we use one version of the right-hand rule. We stick our thumb in the direction of the current, and then we curl our fingers around, and the direction in which the fingers curl is the direction in which the magnetic field goes. What's the equation for this? Well, the real fundamental equation is the Ampere-Maxwell law. What is this? This says that the line integral around a loop of the magnetic field times the little bits of length around the loop is equal to mu naught times the sum of the of the currents going through the loop. That's Ampere's law. Maxwell added a little bit onto it, which is plus mu naught epsilon naught d electric flux by d time. So that applies if there's an electric field going through our loop and it's changing with time, and that's fundamental for explaining electromagnetic waves, but normally you don't need this part. This is the dominant one for most calculating magnetic fields. Okay, so let's try and use that to work out the magnetic field from an infinite wire. This equation is only really practically useful for infinitely long wires or other symmetrical situations. We'll see a bit later how you deal with not infinitely long wires. But if we did have an infinitely long wire, then we can pick as our loop a circle around the wire of radius r, and so the line integral, magnetic field, and the little elements of the line are pointing in the same direction, so the line integral is just the strength of the magnetic field times the distance around the loop, which is 2 pi mod r. And that's equal to, we've got no electric field through this, so that's term is 0. It's just equal to mu naught times the current. So we end up with the strength of the magnetic field is equal to mu naught times the current divided by 2 pi times the distance mod r. Okay, so that's how you do it for a beautifully symmetrical case. What happens if the wire was not finite? Let's say it was 30 centimeters long, a more realistic wire, and turned a corner or something like that. How do we work that out? Well, the fundamental equation we need to do that is the BioSavart law. And what this tells us is if we have a little bit of wire with a current going through it, and let's say that's got some length delta L, current I, and we're trying to work out the magnetic field at some different location with a vector R pointing to it. So what is the magnetic field here? And the BioSavart law tells us the contribution to the magnetic field here due to the current in this little bit of length over there. Not very useful in practice because you can't get a current through a small bit without the current going somewhere else. But what you do is you'll add up lots of these small bits to make a true circuit, and so this is basically our step equation. It tells us the little bit of contribution to the magnetic field from a little bit of wire, and then we'll integrate or sum over a whole bunch of bits of wire, as we'll see in a bit later. So what is the BioSavart law? Well, it tells us that the little bit of magnetic field caused by a little bit of wire is equal to some constants, mu naught over 4 pi. The current in that little bit of wire, the length vector for that little bit of wire with the cross product to r hat, the unit vector in the direction r, or divided by the length of r squared. And that's going to be our step equation for working out magnetic field in most practical situations.